on our social media platforms, which is being live streamed. It's a great pleasure for all of us to have with us Professor Strang, who is a legendary figure in linear algebra. If you think of linear algebra, his books are some of the famous books. He has written nearly 13 books in the area of linear algebra. Recently, I came across a news item where Professor Gilbert Strang and his team, they worked on a tool related to artificial intelligence. And I was deeply interested in this work. And then I contacted Professor Gilbert to deliver a lecture to the Indian audience. And to my pleasant surprise, he readily agreed to be with us on this Zoom platform and deliver a lecture. Thank you, sir. Thank you for agreeing to be with us this evening in India. Professor Gilbert Strang, as I said, is an expert in linear algebra, and he has chosen a topic which is very relevant to the audience in India and also very close to his heart, which is central to his own work. The pattern of this program is Professor Strang will deliver his lecture for about 40 minutes, and then we will have questions from the audience, which Professor Strang has agreed to answer. So with those comments, let me once more extend a warm welcome to all the audience from across India and to Professor Gilbert Strang to deliver his talk. Professor Strang, now it is your turn.
Well, thank you very, very much for inviting me to speak. I received so many pleasant messages from India, and I do my best to reply. And my books are created in Mumbai, so I feel very, very close to India. And maybe you mentioned the count of books, and I can report that there is one more just coming on its way. Maybe if we go to the next slide, you'll see the books that, so the major book is the one on the left, Introduction to Linear Algebra. That's a picture of the 5th edition. And just today and yesterday, we completed the 6th edition. It's not printed yet. In fact, getting paper for printing is a big headache now with the supply chain. But I'm promised some proper printing paper in next month, and so a 6th edition will appear, and you'll recognize the cover because the 4 subspaces, if you have watched any of the linear algebra lecture, you'll guess quickly that those are the 4 key subspaces of a matrix. And then the middle book is the one that connects to deep learning, learning from data. That particular picture doesn't have much connection with learning from data. It was my son was in Myanmar before the troubles there, and took that picture. And it was the best I had, so I chose it for the title. And then the third book is a shorter linear algebra book. During COVID, I thought, well, let's start this course in a different way, in a faster way than linear algebra. So Linear Algebra for Everyone is a shorter book with the essence of linear algebra, with a quick start, and I'll say something about that. So their websites, these 3 books are all on math.mit.edu, and just at the bottom line, I want to mention that the first 2 books, the Introduction and the Learning from Data book, those are also published in Mumbai at Indian prices and that's the contact there. And so I know that, and you can just make that contact or go to that site, and you'll know about ordering directly from Mumbai. Because, yeah. So that's a little bit about myself, but now I'll turn to my two topics. The next slide will be the first slide in one of these topics. So this will be, I'll speak first about deep learning. Please understand that I'm not an expert on deep learning, and I'm not a programmer at all. So my interest is to see what's the mathematics behind it, and a little bit about its successes. I thought you may know, but I thought I would collect here 4 of the great successes in my opinion, of deep learning. The first 2 here come from London, from the group called DeepMind. It's part of Google, but it's a very unique part of Google. And if you're following deep learning and games, you'll know about AlphaGo, their code to play Go. And let's see, I've got a bunch of students in the hallway. I'm going to close them off. Could you guys move on a little bit? So yeah. Okay, so a little quieter here now. So maybe even this first example makes the key point about deep learning and AlphaGo. That is, you don't program the game itself, just the rules, and it plays against itself. 1 million times the machine plays against itself, and it discovers it evaluates the moves, and now it's the best player of Go in the world. Now, at number 2, do you know about the protein folding application? Because that's to me, that's the greatest scientific success for deep learning, and it was done also by DeepMind. The problem of predicting how proteins fold was a very fundamental and unsolved and difficult problem for biochemists, and now the deep learning method has the code computes the way a protein folds. Very, very valuable step in drug discovery. So at the last line there is a lecture that I happened to hear by the head of DeepMind. So you could find that. So let's go to numbers 3 and 4 on the next slide. So number 3 is an older one, language translation. Again, the golden rule is you don't tell the machine all the exceptions. If it's French, you don't tell them all the verbs that are different in French or don't follow the rules. You let the computer discover everything. You just, as you do if you start a game. If you want to teach a game, you just, whether that game, so bridge would be a popular game in the US. And the way to teach it, because there's a lot of theory developed over many years, is you just begin to play it. And then number 4, I have some personal interest in, and it's probably new to you. It's just been published, actually, in the proceedings of the National Academy of Sciences, just a month or so ago. And it's a code which maybe changes the math education, I don't know. Because it's a code that it takes the math, the homework problems in my book, And by chance, it started with my Introduction to Linear Algebra book, and now it's extended to calculus and statistics and differential equations and all the basic college mathematics courses. And it can, you give it the problem, and it can understand the problem and solve the problem. That was a challenge which even DeepMind attempted to meet, but failed. But Ido Drury, do you see his name about the line 6 from the bottom? He's a professor at Boston University and MIT. And there were a lot on his team, but I give him the credit for finding a way using OpenAI's Codex to create software that would understand the problem, solve the problem, could create new questions. I don't know what's going to be the effect of teaching mathematics. How can you assign problems if students can simply go online and get them solved by this code? Well, everything is up in the air on this one. I don't know anything about it, and let me make clear, I'm not an expert on the coding at all. It's just I maybe created some of the problems that they solved and showed that the system worked. Okay, so those are 4 great successes. What do I hope to say about deep learning this morning or this evening? Maybe, so I'm taking it from a math point of view. I'd like to see what is it? What was the critical idea? What did that achieve that had not been achieved before? So what's the critical idea in the structure that's now familiar of deep learning? So I'll explain that structure a little bit and give examples, and then hopefully show you a code that uses it. All right, the next slide should make a start maybe. Yeah, this is the some key facts. Those of you who already know all about deep learning will be beyond this, but I'm one of the beginners, so what's the situation? We're given training data. We're given data. You have to start with something. So you're given data, and you've decided what are the features, like maybe height and weight and age, if these data are people. And then those would be P equal 3 features: height, weight, age. And you're given a number of capital N, usually a large number of large amount of training data. And then we want to create a function, capital F. That's the key to everything. The data is the V0 part, so that goes into the function. And then we have to devise weights X. So X stands for a lot of weights, matrices and vectors that when we put them in the function and we put the input V0 in the function, out will come the identity of suppose we're trying to recognize the numbers 0, 1, 2, 3 up to 9. Then that would be the output from capital F will eventually be one of those 10 digits if we're trying to read handwritten digits, for example. Okay, so everything depends on that function F. And to me, that's the mathematics part. How is that function created? And it's very interesting. So, of course, this type of problem has arisen for years and hundreds of years in mathematics to use examples and to create a function that fits examples. That interpolation, you could call it. or approximation. We don't have to fit perfectly each of the samples V0, but we're choosing coefficients X that we come pretty close. Now, what's the key goal? The key goal is that this function, when you change V0, the data, by just a little, suppose your hand makes a little wiggle in writing a 3, and an extra wiggle is in there, that should not throw off the function capital F. It should still recognize that as a 3. So your function has to be somehow stable against little changes in the data. If I change the data a little, I don't want to get a completely different answer from my function F. And so that's a mathematical challenge. What should be the form of the function? Should it be a Fourier series? That would probably be a candidate. Should it be a high degree polynomial, like a function that has degree 100, like there's an x to the 100th power in the function? Oh no, that's a disaster. We know that high degree polynomials are a very unstable way to fit data. If you move V0 by a little, your 100th degree polynomial is going to change a whole lot. So it's useless. So what was the solution that has emerged out of deep learning? Well, two important points. One is, and some of you will know this quite well, better than I. But so two important points. One is that it shouldn't be an entirely linear function. Those are too simple. We're not going to achieve this with a linear function. But it turns out that if you just introduce this piecewise linear function, you see its graph, it's 0 for negative y, and then it equals y for positive y, and everybody calls it ReLU. Well, that's a crazy thing, but we live with it. So that function is obviously piecewise linear. It has two linear pieces, but it's not a linear function because a linear function just has one linear piece. So it's the appearance of that ReLU at many places in the function, which has turned out experimentally and then theoretically to give the right amount of nonlinearity for good functions F. And then the other key point is, what kind of function is it? Is it a Fourier series? No. Is it a high degree polynomial? No. So F is created from very simple, you see one step there in the box in the creation of F. That's the creation of a part of F, and I'll call it Fk. So the kth little function inside the overall function F. And you see the role of the ReLU, and those AK, and AK is just a matrix. It's one of the weights. We're allowed to choose that. BK is a vector, bias vector. We're allowed to choose that. So the weights are the AK and BK. The ReLU, the nonlinear part, is fixed. And that part you see in the box is one step in this function, in this deep function, which has many steps, like 10 or 20 steps. So that is, in a word, or in a minute, has turned out to be a very successful format for the function. Keep doing a linear step with the AK, then do ReLU on every component of that, then do another matrix A, and do ReLU on every component of that, and keep going. And you get a very general, it's still piecewise linear, but oh, so many pieces. By the time you've done 10 of these functions f in a row, the number of pieces of linear pieces is climbing way up. So it's a function that looks like a kind of mosaic. I don't know if that's the best word in English to choose. It's like it's made out of like little flat pieces, but millions of little flat pieces. And that has turned out to have this stability property that is so critical and now achieved in such an unusual way. So that's my little speech about the form of the function. The form of the function is repeat this simple sort of thing that's in the box. That's just one step. Repeat that to 10 steps or 20 steps. That's the depth of the network. And you get something that's still always this mosaic, piecewise linear, but many, many small pieces, and it's successful. Okay, so maybe the next slide is, let's go to what comes next. Yes, this is a picture of a little sort of illustration of that piece. You at your inputs are those V's on the far left. The multiplying by a matrix A combines all the V's into AV. That's the next column. Then you do these ReLU, you add the B, and then you do this ReLU stuff. I've indicated that with a plus sign. That, remember, that just keeps the positive parts, positive numbers, and zeroes out the negative numbers. So that is one layer, one function. And you could see that you had 12 matrix entries to choose and 4 B's. So maybe you have 15 or 16 coefficients to pick just for that one function, and then you're going to do a function of that and a function of that. It's the chain. A chain of functions is a good word. And the derivatives, of course, you're going to need derivatives. Just think for a minute. You're optimizing these A's and B's. So what's the great principle of optimization of a function? Derivative equals 0. I'm not a big fan of calculus. In fact, I write in my online, I put too much calculus. I think at least American students are subjected to calculus and then calculus 2 and then differential equations. And many times they don't learn linear algebra, which is more important, or at least as important as calculus. So anyway, this chain rule is something that you learn from in calculus, so that calculus does contribute to the world. And the chain rule is the derivative. And why do we want the derivative? Because we're trying to optimize these matrices and vectors. And if you want to achieve minimum something, you have derivative equals 0. You need derivatives. Okay, so that is the mathematics. And that top line shows you my point about a chain of functions. You apply F1 and then you apply F2 and so on. You apply L functions. And it's a process. It looks like you have many unknowns and many derivatives you do, but there's a brilliant idea, a fast way to compute, which we won't do here. Okay, next slide. Now this is, anybody, if you don't know this slide and you're interested to see how things work, just go to this playground.tensorflow.org. Some chap from Boston, I'm glad to say, created it. He worked for Google, and he created this website. If you know it, then that's all to the better. So the website has 4 samples, and we're going to that you can run and you can see how it happens. So let me tell you before we do anything. Let me tell you what. So up at on that top line, we've made choices like ReLU. We chose ReLU. We've chosen the learning rate, the step size, and the optimization. So math things. Then on the far left, you have a box, you see the little box with inside it is some orange dots around a circle full of blue. So we want to separate the orange from the blue. The orange is the negative data, the blue is the positive data, and we want to create a function f that's positive on the right one, on the orange, and negative on the blue. Right. So, and that function is going to have to be in our sort of linear chain of, have to be a chain of linear functions. So you see there, so that the box there is around one of the 4 examples that this website offers, and we'll try that one, and we'll try one more. This one is not that hard. So look over on the far right. So Andre has just started the system. So do you see up on the top line, it's counting the number of times that it has cycled through the data, cycled through all the points. So it doesn't take it long. We're up to 1,000 cycles already. An epoch, that tiny little word up there is epoch, but that means cycle. So now we're up to 1,500 cycles. What are we doing here? It's not doing well. It's the graph of our function f, which is supposed to be one color on the blues and the other color on the oranges, is not doing well. Andre, I think you have to give it more pep, more neurons. So could you add? Yeah, that's great. Maybe add, yeah. Let's see if that's still not very many to have only 2 layers. Oh, that did it already. That was sufficient strength, sufficient number of weights. So you see, we added one more to each layer. We only have 2 layers still, but we have one more function at each layer. So this is a very small network, but it wasn't that hard of a problem. And you see the function, well, the graph of the function. You're seeing a sort of graph. You're seeing where the function is positive in the orange area. You're seeing where it's negative in the blue area, and you're seeing where it's 0 in the white. So that white is interesting. So it's made up of straight lines, and you say, why straight lines? Well, because everything was piecewise linear. Everything was created out of linear functions and ReLU. So I hope you're satisfied with that solution. That function achieved the goal. It was positive on one and negative on the other, and that's what we wanted. So it tells the type. Now is going to come a more difficult function. Second one is another example. You see up in the left corner, we've gone to a different example. And this example is a bunch of spirals weaving in between each other. Now, Andre has given 3 layers, and he's put 4 neurons on each layer. So that was fine. We could stay where you had it, Andre. Yeah, 3 layers, and let's have another layer. Go back to the spiral one, not the first example. That's it. Yeah, we wanted to go there. Okay, so we're trying to find a function. You see how difficult it is, because these the orange is spiraling within the blue, and we have to separate those with a function. So we haven't. Let's make it go. Yeah, I don't think we've given it enough to work on. Let's see what it does. It'll try. Yeah. I'm not seeing the picture I expected to see. Yeah, here's the picture kind of beginning to come. After all, the code is still running to improve, but you see the difficulty to get the blues without the oranges when they're all spiraled in together is a real challenge, and we're not going to achieve it with this set of 6 neurons. So let's add more. Add maybe 4 to each, 4 in each. Yeah, thank you, Andre. All right, now start it again. Okay, cycling through. Now it's going to do possibly better. We'll give it a little time. I'm not going to, yeah, I'm there. You see now it's created a more complicated function that's doing its best to follow the orange spiral and the blue spiral, but it hasn't achieved perfection yet. Yeah. So this is quite fun and quite instructive. And to have any idea of how many neurons are needed to do the job. So I'll just say for this one, if we added another hidden layer, say up to 4, and if we added another neuron, so up to 5 neurons on every layer, it's doing better now. Sort of, yeah, that's definitely better, but not success. Yeah, and okay. So don't forget this website, playground.tensorflow.org, because it shows the idea in action. Okay, that's pretty much what I wanted to say about deep learning, to give you an idea of how it succeeds by having this chain of very simple functions, and it has stability. And then it can eventually get successfully very complicated functions. Okay, may I do a little bit of linear algebra in the last minutes here? So this would be the way that the new 6th edition starts. This doesn't appear in the 5th edition, the book that's known. The 6th edition, not yet printed, but I have papers that use this factorization. Does everybody know that? So those are matrices. A is a matrix, a completely general matrix, M by N. And C is a matrix. So the factorization is A turns out to equal C times R. And C and R capture important parts of the matrix separately. So if you read the 3rd line there, C contains the first R independent columns of the matrix. It's just natural to have R columns times, when I say R columns, I mean little r, like maybe 3. If the rank is 3, if there are 3 independent columns in A, but A could be a big matrix, 10 by 10, but maybe just 3 independent columns, and the other columns are just combinations of those. So then mathematics says, hey, separate it out. Get the parts, use the independent columns in C, and then R tells you what combinations of those columns give the columns of A. I've just said in words what matrix multiplication is about. Part of learning linear algebra is really understanding matrix multiplication. So C times R produces combinations of the columns of C, and the combinations, the weights in those combinations are given by R. So we only need the small r, the rank, tells us how many columns we need. And then and then that decides C. So C contains independent columns. Independent columns means that none of the columns are combinations of the others. They're all fresh and new. And then now, and that was good to see about R. So let's go to the next slide. Yes. So we'll talk about this and so now, so what are dependent columns of the original matrix? Well, C used up a full set of independent columns. All the other columns, the n minus R remaining columns, are combinations of the C columns. And that's what the matrix capital R just does. So if you look at the middle of that slide, you'll see the whole thing in the best way I can describe it. So we start, are you looking at that long math line there? A equals C times R. Now C is the independent columns. Then we have the identity matrix, and then F, the combination matrix. So that we have that the identity CI gives us the independent columns, and CF gives us the dependent columns. And just in case they didn't come independent first and then dependent, I need a matrix P called a permutation matrix that just puts them in the right order. So there is A equals CR. And what I want to say is that in the new 6th edition, it becomes the fundamental way to understand the solution of linear equations AX equals 0. That's looking for combinations of columns of A that are 0, or AX equal some right-hand side B. Remember, AX equal B is standing for M different equations. M could be 100 or 1,000, and X is standing for the weights on the columns to give the correct B, to match the correct B, the right-hand side. So this is the key to solving AX equal B. That's really what I want to say. And it's known, of course, this isn't the first time AX equal B was ever solved in linear algebra. It's or the last time either. But so AX equal B. And what's the underlying method here? How do you find C and R? Well, that's called elimination. So that's a method that goes back to China and India a zillion years ago. Elimination, you simplify the matrix by getting zeros in it. And but what I wanted to do here, so this is my goal, and I'll stop at this slide. What I wanted to do here was to understand elimination at a matrix level, instead of only understanding elimination as a bunch of little steps, subtract this from this and get a 0, and then subtract this from this. If you've studied linear algebra, that you were exposed to elimination, the idea of elimination. But this is a picture that, for me, starts the book with the ideas of independent columns and dependent columns, and matrix multiplication above all. Matrix multiplication is quite subtle, and there are different ways to do it. But the most useful way tends to be a matrix times a vector gives you a combination of the columns. A times X is a combination of the columns of A. That's the mantra to remember. Okay, by the way, you haven't missed anything in the remaining 15 slides. Maybe we could jump to the very end, Andre, if you want to. So these are examples. Of course, the textbook would do all these examples. So yeah, so this is creating C, examples to create R. Oh, stop here for a minute. This is the big picture of linear algebra that I'm proud to say was introduced in the first edition of my linear algebra book. So it has the four subspaces. We won't go into subspaces here, but it's a fundamental idea. And these are the fundamental subspaces. Yeah, so that's a picture of linear algebra to learn, in my opinion, as you learn the subject. So this is still very basic linear algebra. Let's keep going now to next slide. Yeah, this is, now something called singular vectors showed up. We could keep going to 23. Here's, now I'll take a minute to so we started with A equals CR. That's the beginning of linear algebra. Now we're coming to the highlight of linear algebra. It's called the singular value decomposition. And it says every matrix can be thought of in 3 steps. A rotation, 3 easy steps produce any matrix. That's just magic. A rotation, and then a stretch. Do you see this? The rotation, we still have a circle. Then when we stretch the axes, we have an ellipse, and then we rotate the ellipse. So those are 3 matrices: a rotation matrix, a stretching, which is just a diagonal matrix, and a rotation. And there's the bottom line is showing that we have 4 numbers in the matrix, A, B, C, D, and that 4 matches the 4 numbers in this factorization. There's a rotation angle theta, another angle phi, so 2 rotation angles and 2 stretches makes 4. So that's a ridiculously fast sketch of this famous final step in a linear algebra course, the singular value decomposition. And now maybe just the final slides. Okay, this is applying the SVD in something called principal component analysis. It's useful in finance, many Places. And the last slide is more about PCA and singular values. Yes. Okay, so that's that. I'll stop there. Actually, and go back. Maybe Andre would carry the slides back toward the beginning, and I'm happy to try to answer questions. Thank you. Thanks for your patience.
Right. I'm just removing the screen sharing.
Yes.
I have received a couple of questions.
Okay.
Question.
Do our best.
At the boundary of machine learning, neuroscience, and philosophy. So this questioner is asking, can machines ever become conscious or self-aware?
Well, now that's a question for a philosopher more than a mathematician. A mathematician is trying to become aware himself. So the mathematician is inserting himself or herself into the set of ideas that we have here and trying to organize them, see them clearly. I don't think I have an answer for. Of course, the great problem of science, not yet solved, is how the mind works. At least that seems to me the outstanding problem. And does the mind do anything like the process of deep learning? Because whatever the mind does, it has to have these properties of stability and generality. Anyway, I'm not enough of a philosopher to give intelligent answer to that question, but it's a good question.
Right. If there are any questions from the audience, you can raise your hand. I will unmute you. Then you can put your question. You can also raise your hand electronically.
Okay.
I'm just looking for the electronic right. Professor BJ Rao, could you please go ahead with your question?
Yeah, Professor Strang, I really enjoyed your talk. I want to ask you a non-mathematical question. Am I audible?
Yes, perfect.
The question is, when you kept on increasing the number of processing centers, such as neurons,
yes,
output pattern that you were getting were highly unpredictably variable.
yes.
Is that the consequence of processing being time evolving, or is it the consequence of randomness in the output itself?
Well, I suppose the variability depends on the data, of course. It might be interesting to see, because we never had a look deep inside that function to know what those weights were that it chose, or how long it took to choose them, how many steps it took to compute good weights, which is the big calculation. It can take a week on a supercomputer, on a really big example. So we couldn't possibly look inside at that step. Yeah, it's a challenge that we're able to do it at all, to complete the calculation. I think it would be, I mean, so if you ask make it a mathematical question, are there patterns? That's what a mathematician is looking for, patterns. Are there patterns in the numbers, in the weights, let's say, that reflect patterns in the data? What's the link? Always, what's the mapping between the data and the function you're creating, the approximate function, those weights in the matrices? And that's very delicate. I don't think there's a lot left to learn. Maybe I'll just answer that.
Just want to add one more thing. The reason I asked this question is the system going from chaotic to non-chaotic systems when you increase the number of neurons?
Oh, that's a good question to ask about. Sort of the asymptotics of increase the number of neurons. Yeah. So I haven't conducted an experiment to give you an answer, but it would be quite reasonable to do so.
Yeah.
What happens if you? Of course, we have to be careful that our numbers are stable. If we run into an unstable thing, then we just lose track of any pattern. But the marvel of deep learning is that the process does seem to be remarkably stable, and it kind of grew out over the years. It looked for some time as if the whole idea of AI and thing was not going to succeed. Say before the year 2000, roughly. They had ideas, but they weren't stable, and therefore they didn't work. And then gradually inspiration came to a number of people all over the world contributed to find a stable construction of the learning function f. Yeah. So the answer, as you will have expected, is that I don't really know. Yeah.
Right, sir. Professor Strang, there is one question from the audience.
Yes.
Is there any deterministic way to identify the right number of layers, neurons, and activation functions?
Yeah, well, now it's not impossible that there would be, but I'm guessing that in real life, experiment is probably in this area. Experiment is probably the fastest and best way to decide how many, what shall be the depth. The depth, well, so analysis is going on with a lot of people working on it. It's turned out that the ratio of depth, which means the number of layers, to width, which means the number of neurons on a layer. So you saw both of those. You saw 3 layers with 4 neurons on a layer. That ratio of depth to width is a critical quantity if you want to understand the big picture. And I don't claim that I do, but I know from experts that that ratio is a critical quantity. Yeah. I think that's all I think of to say. It's sort of expressible in language that we've been using this hour.
Right, sir. There is one more question.
Sure.
It says that, well, decision making, when we talk about learning and artificial intelligence, decision making is something that comes to our mind. And as human beings, most of the time, we make our decisions based on logic. Maybe sometimes we don't use logic, but often we use logic to make our decisions, logical thinking. But there is also intuition. Sometimes people arrive at the final conclusions without going through logical steps, but they arrive at the final step. So is there a place for intuition in machine learning also?
Yes, so I guess intuition is maybe you certainly have taken some steps. The thing is, you don't really know what they were. You didn't predefine the steps, but somehow you took some steps. And I think there's certainly, I'm sure that deep learning has become more and more successful by people saying, why don't we just try this? And for example, one example that pops to mind is Dropout. So one of the great founders of deep learning proposed Dropout. So that was simply a way to reduce the computations by leaving some of those neurons out. After you've begun the computation, you think, I don't need this one. I'll try Dropout. And that has succeeded. But I don't know what pattern he would use in dropping out. So I guess my thought would be that intuition will suggest some new steps, and it already has, and it will continue, and people will try them. And if they fail, they won't write a paper about it, just go on. But if it works, they will tell the world about, well, look, try this. And that certainly has happened and will happen. So I think there is a role for intuition.
Right. There is one last question, Professor Strang. Among common people who are not so familiar with machine learning, deep learning, there is a mention that what will happen if machines take over human beings?
Yes, I understand. Well, I don't think I have any deep answer to that. Obviously, we are going to gradually, and over years, we're going to understand better how machines work. We're going to understand better how our mind works. At the same time, new things are happening. We could say we're being taken over by machines, but also at the same time, we're understanding those machines. So we're catching up with them. And as people invent a new machine, if it works, then everybody wants to know, why does it work? So mathematics will always have a part there. And it's been an exciting time to try to understand. You understand what the deep question, what you want to explain is, why does this function that you create out of the learning data, why does it do a good job on data that it has never seen, on test data? That's the question of generalization. How is it that the function's able to generalize from what it has seen to data that it has never seen? And that's being understood better and better. A lot of talented people have gone deeply into these questions and are doing so more, and of course, highly active in computer science and partly in mathematics. So I'm glad that linear algebra plays a part, but I realize that ReLU makes it nonlinear, and that's turned out to be absolutely fundamental and desirable. Okay, thank you.
Professor Strang, is it okay if I take one more question?
I guess so. I'll tell you if I have anything any thoughts.
Professor Nehal Ahmed, could you please go ahead?
Yeah, sir, I have two questions. First is, we have seen randomization in neural nets. So my question is, what if we randomize, we fix the weights between input and hidden layer, and then we randomize some weights between the hidden and output layers?
Well, so the whole question of randomization is an interesting one. Maybe this is my final answer, since it's important to understand. Up until 10 or so years ago, linear algebra was all about, it wasn't random. It was all about finding a fast algorithm, fast and stable, to get a result. And we've achieved, we being the numerical analysis community, which is worldwide, we found ways to compute the eigenvalues of a matrix. At an earlier stage, everybody knew what the definition of an eigenvalue was, or an eigenvector, but how to compute them? Well, 10 by 10 matrix was already a problem. So, but now we have good algorithms to compute the eigenvalues of a 1,000 by 1,000 matrix. But still, 100,000 by 100,000, that's still a major challenge. And our methods simply take too long on a really giant matrix, and that comes up in different applications. Big matrices, too big to multiply. Think of that, matrices that are too big to multiply. So, but the answer, there has been an answer of randomization. Sample the columns. Don't take all zillion columns. Take a sample of the columns and work with that. And then if the matrix has reasonable structure, it's successful. It works. So randomized linear algebra, RLA, is a open door to ideas that were unexpected. So there was the period where we couldn't really do any calculations, then the period where we could do pretty amazing ones, and now randomization is leading the way to even bigger problems. Well, I think that's probably everything I know, and I hope this has been helpful, and I hope you'll see enjoy linear algebra.
Absolutely, Professor Strang. It was a pleasure listening to you. You explained in a very, very simple language And you took so many questions from the audience too, and it was a very interesting conversation. I would like to thank you on behalf of University Grants Commission for giving this wonderful lecture and for spending almost nearly 1 hour with this audience. Thank you very much, sir.
And thank you for inviting me. Good. Best wishes.
Thank you.